All right, I think we're live at 5 o'clock. So hello everyone and welcome to the first edition of the Marine Studies Group Careers webinar. It's very good to see so many of you. I think there were over 300 people who signed up, so welcome everyone. I'm Iris Verhagen. I'm a lecturer at the University of Liverpool and I'm also part of the Marine Studies Group, and I'll host today's webinar where we will talk about how marine geoscientists are helping to solve the climate and environmental crisis. Marine geosciences is the study of the bottom of the ocean floor, and our four panelists today will go over what they are doing to help out. The webinar is live on Zoom and also on YouTube. You can see the links on the slide here, and we will be taking your questions as well. Before I go and give our speakers a chance to give their talk, I wanted to briefly tell you about the Marine Studies Group. So we are a special interest group of the Geological Society of London, and we are all about encouraging research, teaching, and public understanding of marine geoscience. And we do that by arranging scientific meetings and workshops, and also events like this webinar today. So how is it going to work? Today, the webinar will run for 1 hour from 5 till 6. We'll start with 4 short presentations after my introduction. And then after those presentations, we will take your questions. And so that will be for about half an hour. Please submit your questions. If you're joined via Zoom, please use the Q&A window for that. If you are watching on YouTube, please use Twitter or Instagram or the email address as well to submit your questions. So you can find the email address in the comments on YouTube. We will try to answer all your questions if we can, but please also indicate your favorite questions. So if you are in the Zoom meeting, give a thumbs up to the questions you want to get asked, and we will prioritize the ones with the most likes. So first of all, we have Michael King. He is going to talk to you about his current job. So he did a master's at the University of Liverpool, a 4-year degree course, and he is currently working at Ocean Infinity. His first job, however, was with Baby Hydromap, where he started working as an offshore geophysicist, but now he's working in the world of marine robotics. So take it away, Michael, when you're ready.
Yeah, hi everyone. Thanks, Iris. So I wanted to talk about, firstly, why do we do what we do? Because that's kind of critical to understanding how we do it. And firstly, understanding more about our oceans is critical to lots of areas of our lives, from understanding the way the world was formed and how it behaves, to understanding the impact of our lives on the planet. And crucially, these days, the majority of our energy sources come from the offshore world, be it offshore oil and gas, offshore renewables, tidal power, wind power, and understanding the seabed has never been more important in these endeavors. But how do we go about investigating something that we can't see or touch? How do we work out what the seabed is made of? Is it rock? Is it sand? Is it mud? How do we find out if we can use it or build something on it or dig it up? We mostly do this through the use of acoustics, which is using sound waves to measure properties of the seabed that we can then turn into very detailed maps and charts in order to inform further campaigns. To begin with, it's really important to establish exactly how deep the ocean is to a very high degree of accuracy. Modern technology actually allows us to work out the depth to the nearest centimeter, which is pretty impressive when you're talking about the depth of the full ocean. So we use ships with bathymetric echo sounders to send out high frequency sound waves that bounce off the seabed. We then listen for this sound, and the amount of time it takes for the sound to travel to the seabed and return again allows us to work out the depth very, very accurately. Quite often we send out thousands and thousands of beams of sound at once to allow us to map very large areas very quickly, and we use advanced processing algorithms to work out which acoustic beam is which. So that's the depth and the seabed topography, which is the first step. After that, We also need to look underneath the seabed. As you'll hear later, if you're building anything offshore, you need to understand the subsurface to make sure that it will stand up to the construction of offshore structures. And this is where seismic equipment comes in. So by using slightly lower frequency sound waves, we can actually send them into the seabed itself, where they bounce around and reflect off different layers of sand or rock or mud, and then return to sensors behind the ship. As before, accurate measurement of the sound travel time and the angle of return allows us to build up a really detailed picture of what is actually underneath the seabed. Different rocks and sediment densities make sound behave in different ways, and by sending out multiple sound waves and listening for them all at once, we can actually build up a really good 3D model of where all the noise goes, and we can work out what the layers look like underneath the seabed. There are, of course, many ways to remotely image the seafloor, but the third and final one that we use most often is called Sidescan Sonar. This involves towing a high-frequency sonar system quite close to the seabed to send sound waves out almost horizontally. These sound waves then bounce off different surfaces with different intensities, almost producing a photo-like image of the seabed that you can see there. Using this data, we can work out the size and shape of any objects, whether they're natural or man-made. It also gets used a lot to check on the condition of existing structures to make sure they're not damaged. We can even tell how fine or coarse different sandy sediments are from this data, which gives us loads of geological information to inform the other project elements. So that's a really brief summary of what data we collect and why. And these data sets have been collected using specialist ships for many, many years. But what does the future hold? And how will this data be collected by your generation of marine geoscientists? The company that I work for, Ocean Infinity, are world leaders in the use of robotic systems to collect all of these types of data that I just showed you. We deploy predominantly autonomous underwater vehicles. They're like robotic submarines without any people on board. They're equipped with the sensors I mentioned earlier, which complete surveys in very deep water, where the use of normal ships just wouldn't get the required detail or resolution. We deploy these vehicles in fleets to rapidly cover wide areas of seabed, or to provide many different data sets at once. They're monitored and controlled from a ship on the surface, but through the use of automation and a little bit of artificial intelligence, they actually navigate themselves and make some decisions about their behavior without human intervention. We also have fleets of robotic ships. Some of them are small, maybe the size of a car, right up to proper ocean-going ships the size of a proper craft. These deploy the same equipment and can collect the same data that those conventional vessels do, but we drive them via a satellite link over a remote controlled network. This means that we don't have to send anyone offshore anymore, and this provides some real benefits in terms of environmental impact and safety. The same data is collected from these robotic ships, as I said, giving us the same answers about the seabed as before. We're just trying to take data acquisition into the future and provide the next generation of tools to carry out this work. All of the vessel command and control information, as well as the scientific data itself, is handled in one of our remote operations centers, where a large team of experts is involved in the running of the projects. Each vessel is piloted like a big remote control ship, with all of the diagnostic information and system feedback provided to the operator within their pilot station. As you can imagine, this is one of the most technologically advanced setups anywhere in our industry and relies on very, very advanced IT and satellite information communications infrastructure. How we handle these vital data sets that our ships provide and how we deal with the information I mentioned is critical to the end uses of the data that you'll hear about in the next few talks. But what I wanted to get across to you today is that the use of the most modern technology available is shaping the way in which we, as marine geoscientists, are working both onshore and offshore, and how the advances in robotics and computing are making our jobs safer. They're making our jobs more environmentally friendly, and frankly, they're making them more exciting. We get to work with some of the coolest and most advanced technology on the planet, and we get paid to do it. So I look forward to some of your questions in a little while, but for now, over to the others.
Thanks very much, Michael. We're just going to swap the screen so that we can introduce the next speaker, which will be Katrine. So Katrine has done her undergraduate in Belgium, so there's no A-levels there. So we did have a question in the chat already here about which A-levels are the most useful. So we might come back to that in the discussion later. She did a PhD at Cork University and is now working as a lecturer in Bangor. So she started at Bangor, then she moved briefly to Liverpool, and she is now a senior lecturer at Bangor. So Katrine, when you're ready, you can share your slides and tell us what you're up to.
Oh, well, good evening, everyone. I hope you can see my slides. Can you see that? Yes, a nod from Iris. Thank you very much. Hello, so I'm Katrine van Landingham. I'm a marine geoscientist, and it is really all about making noise. And I think Michael introduced that really nicely. So we should really talk about the crisis first, the climate crisis. How does that really affect the ice that meets our oceans? How does that ice retreat affect humans? And how can we as marine geoscientists help at all in this crisis? So in this case, how could we investigate that ice retreat? So if you want to learn about the scientific basis behind the climate crisis, then I could highly recommend the reports by the Intergovernmental Panel on Climate Change. They are published every few years, and it really delivers that scientific basis, but not only of what the climate crisis consists of, but also what the impacts are and what the possible responses may be. Now, this is a meaty report, yes? So if you wanted to cheat a little bit, luckily there are people who create infographics, and I also provide you with the link to those, some of those infographics, and I present a few here. So because the globe is warming, the global warming is absorbed a lot by our oceans. So our oceans are warming, and a lot of our ice is in contact with that warming ocean. So not only does the ocean body actually get larger, because a warmer ocean body will actually be more voluminous, it will also make the ice melt. And in fact, the ice sheets and the glaciers melting is the dominant source of sea level rise. Is that a problem? Well, yes, a lot of people will be now hit by, by flooding, and a lot of people don't have the means to actually have alternatives. So just in Bangladesh alone, you'll have 18 million people who will be displaced if we have this sea level rise continue as the way it does now before 2050. So the impact is enormous. Now, there is recent coverage of these retreating glaciers, of this retreating ice, so it does become indeed more mainstream knowledge that this is indeed in crisis and that the ice is retreating very fast. So the problem is the present day ice sheets are indeed retreating very fast, but what is driving that? It's climate change, but what else contributes to that retreat? Might we expect different rates of change, and why would that be? Sometimes quite difficult to look at present day ice sheets because it's difficult to go and look underneath. So we look at paleo ice sheets from the past. And here in Britain, we were in fact covered by ice about 20,000 years ago. And the Irish Sea ice stream was one of the main ice streams that was draining that. And that was also in contact with a warming ocean after, of course, the last glacial maximum had peaked after its coldest period. So that's what I look at, and other marine geoscientists. We help discover how this ice streaming changed in the past. And so therefore we might look into the future, and we might be able to predict better what might happen in the polar ice caps. But then with sound waves, and yes, I think we can all appreciate by now that it's very, very, very important to communicate correctly, that you have good information out there, that you fight misinformation, and that you use these platforms of communication like the social media outlets very carefully and very wisely. So sound waves, making that noise by social media, for instance, is really important. But as Michael just introduced very nicely, we can also use a different type of sound wave that comes emitted from an echo sounder that is attached to a vessel. So this is an image of a multi-beam echo sounder that has a fan of sound and that allows us to form a topography image of the seabed. And that allows you to look at the landscape of the seabed, because the landscape isn't just the terrestrials. We have landscapes also in the oceans. So how about we have a look at a paleo ice stream and the landscape that left behind. We don't even have to go very far. This is just to the north of Anglesey, and this is what the shape of the seabed looks like there. So you see it's not flat, it's full of little hills and mounds and pits and things like that. And of course then as a marine geoscientist, I look at those and I identify them. So I have megascale glacial lineations, rib moraines, I have fluted rib moraines, I have drumlins, fluted drumlins, I have push moraines, and iceberg scours. And yes, indeed, those icebergs 20,000 years ago have left marks on the seabed then that you can see now, okay? So all that information is still there, and you'll have to kind of trust me on this one. I can then use all that information to reconstruct what the ice did 20,000 years ago. Was it retreating fast? In what direction was it retreating? Was the bed frozen? Was it thawed? So we can learn about the mechanisms as to why all those changed as the ice was retreating. So we might then learn what might happen in the polar regions of today. But yes, we might want to go there then, though, mightn't we, to see what happens over there. So we have to go from the Irish Sea to Antarctica. That's easy peasy lemon squeezy. You only sit on a plane for 24 hours and then you take your vessel through the Drake Passage. I cannot recommend it. It's like a washing machine. And if you're already seasick like myself, it is not so pleasant. However, the reward is great because the Antarctic environment is mesmerizingly beautiful. And I shall skip through a few of these beautiful images that I took in 2017 just to convince you how serene and beautiful it is. These are massive icebergs. And then we arrived in these fjords. In the West Antarctic Peninsula, you have many fjords, and a lot of these have seen ice retreat very steadily in the last few decades. I mean, here in this image, you see Bergen Bay, so one of those fjords. You have an orange line there that says it's from 1955. The glacier front was actually 2 kilometers further out than what it is today. So a steady retreat of a few kilometers in the last few decades, and we can map all that. And I then contributed to mapping that seabed once again, the topography of this bed in this fjord. And that allows us to understand why the retreat was what it is, why is it different over time, why is it different over space. And I'm not alone on that vessel, of course. I work with biologists and oceanographers because, of course, it's a holistic science to try and understand this ocean and ice environment because all these processes are very linked. So that's why we're all working on that together. Yeah. What the multi-beam echo sounder also does, because it's a fan of sound, it can actually capture the actual ice front. So not only do we see the bed, but we see the edge of the ice. And that shape will also identify, or well, it'll identify to us what type of retreat might be expected. And if that changes over time, again, we try to understand why that is, and if the glacier is in danger of further retreat because of the changing in the shape of that ice front. So these sound waves are a very powerful tool for us indeed to reconstruct the environment in the past and the present. And in fact, last year, I wasn't on board then, but the team that was on this project saw a calving ice front. They had to run out of, well, not run, but steam out of the fjord very, very fast because all that ice, a wall of ice just came out. Now, some reporters from Sky News were on board and they reported on this. They missed the main event, in fact, but they were still able to film some of that ice collapse. So have a look at this link and you'll see what it really looks like when an ice wall like that comes down. So that's really exciting on one hand, but it's also giving us this urgency really, you know, this is retreating fast and we can't have that. We can't have the ice retreating like that. It's very nefast for the sea level rise. So to summarize, I'm a marine geoscientist and I'm using sound waves to make the right kind of noise via social media. I'm not the most vocal, but I try to. But I remotely observe the ice retreat in the past and the present. And I feel my role is that I should help quantify the consequences of the climate crisis and understand what is to be expected in the future. And that quantification really should be enough in itself because that gives confidence to the message that we should all be vocal about. And then we can convince people that it really is very urgent that we respond. And yeah, but I'll leave it at that. Looking forward to your questions and I'll stop sharing.
Thank you very much, Katrine. Those are some amazing pictures from Antarctica. So next up we have a presentation from David. David has got A-levels in maths, physics and geography. He did his MSc or 4-year course at the University of Oxford. He started his career as a geotechnical engineer at Fugro, and he is now director and co-founder of East Point Geo, which is a geo consultancy company. So when you're ready, David, please share your screen.
Thank you. Okay. Hello, everybody. Hopefully you can see my screen now. So I'm going to talk about marine geohazards, so hazards to developments in the marine environment. So firstly, what things get built in the marine environment? Well, major developments include a lot of infrastructure relating to energy, so offshore wind turbines, oil and gas platforms, cables connecting that infrastructure to shore, or taking infrastructure from one country or continent to another. So pipelines, interconnected cables, and also, very importantly for our modern world, intercontinental telecoms cables. So this map up here just shows a plan of the spaghetti of cables that links us together and helps us communicate and helps us have discussions like we're having on this call today. So what's the cost of building in the marine environment? Well, this graph up here, it shows the cost of various different energy supplies. And I'm going to draw your attention to the red line, which is offshore wind energy, versus the blue curve here, which is onshore wind energy. Now you can see back in 2017, there was a large difference in the cost per hour of a megawatt of electricity between those two sources of electricity. Now that cost has come down through time, and that's because of technology developments to specifically try and make offshore energy, offshore wind energy cheaper. But fundamentally, to put the same thing in an offshore environment tends to be more expensive. So why is that? Well, access for one. You have to do everything via a boat, which is a lot more complicated than moving around on land. It can be quite a harsh environment, strong seas and strong winds, and infrastructure requires larger foundations to sort of bridge the gap between the sea level and the water bottom. So for that reason, developers of these objects, this infrastructure, are very keen to protect the structures that they build from these hazards. So what kind of hazards exist in the marine environment? Well, some are very similar to those hazards that exist in the terrestrial onshore environment. Landslides, for example, is an image of an onshore landslide, and these are images using techniques described from the previous two presenters in the offshore environment. So very large movements of seabed, in this instance 1 kilometer wide. In this example down here in the bottom left, we've got an area around about 0.5 kilometer wide that's breaking up and sliding down slope. And these can mobilize on very shallow slopes. Mud volcanoes, like an onshore volcano, but spewing out mud rather than hot lava. Storms that result in submarine mud flows that, in this example, during Hurricane Ivan back in 2004, knocked over an oil and gas platform onto the seabed. And other turbidity currents and debris flows, much like avalanches that we know from the onshore environment, but happening in the offshore environment with muddy sediments. So I'm going to run through a few examples of hazards and what we can do about them. The first example is termed mobile seafloor. So what do we mean by mobile seafloor? I'm just going to play this short video, and here we have a pipeline on the seafloor that was originally buried. It was installed and buried below the seafloor. Now, due to the loose sand on the seabed and currents in the water that move this sand around, we end up with that seafloor becoming mobile. And in some cases, we have these large sand waves and sand dunes moving across the seabed and unburying some of the infrastructure. What's the problem with that? Well, you get hollows created underneath the pipeline. And that can leave the pipeline just hanging in the water column. That leads to excess of buildup of stress in the pipeline, and it can lead it to ultimately breaking prematurely. What can we do about that? Well, the main mitigation is to go and place rocks, small rocks to act as a sort of natural support underneath the pipeline in places where the original support has been removed. But this can be very costly, and in some cases, the gap that develops can be several meters, up to 10 meters. So by performing some geoanalysis, and the image up on the top right shows some detailed morphometric analysis of seafloor imagery, looking at where scour hollows are occurring. So that's the blue shades. Looking at areas where there's mounding up and increasing sediment thickness on top of the pipeline, that's the red, and also trying to map the increase in the scoured areas through time, so that's the sort of yellow through to red lines, and also mapping some of the sand wave crests that are moving across the site, and those are these straight lines here, to give us an idea of how the seafloor is varying through time. And ultimately to help us advise on where it's worth putting in the remedial measures, such as placing rocks underneath the pipeline, and where it's the phenomenon is just sort of too large for that mitigation to be effective, and other measures should be used. This bottom image just shows the size of some of the movements. So we've got a profile of a sand wave here. So the very light blue shade shows a sand wave, which at its shallowest is 22 meters below the sea level, and at its deepest is about 26 meters below sea level. Through time, that same sand wave has been surveyed many times, so from 2016 all the way up to present day. And you can see how the trough here moves from about this location to the black line here. So we're talking sort of something like 70 meters movement, and the peak is shifting similarly. So we're talking really quite large movements across the seabed. I'm just going to move on to a second example, and this is relating to cables installed on the seafloor that can be damaged if they're not properly protected. Now, in this case, the main hazards are typically related to human activity, and specifically shipping. So let's just take this example of a planned wind farm off in the marine environment. So we're in the just offshore the coast here. And that infrastructure, it's a wind farm, it generates electricity, and so it needs a network of cables to transport the electricity back to the shoreline. But let's consider one dredging vessel's 1 day's activity, going backwards and forwards. Now, most vessels are obliged to transmit their position on a regular basis, so you can work out what the traffic is like. So that's a repeat pattern of a dredging vessel back and forwards for 1 day. That's the pattern for a full year's worth of dredging vessel activity within the vicinity of the site. If we then consider tugboats, that's all the tugboats that have gone across the site in 1 year. Those are all the container ships, and those are all the fishing vessels. So you get the idea, there's a lot of traffic crossing through this site. So how do we avoid this problem? Well, you can typically bury the cable to avoid anchor strikes, but the question is how deep? The deeper we have to bury the cable, the more expensive it becomes. Well, the solution is to assess the probability of an anchor strike. So that is dependent on the exposure of the cable to how many vessels, and that's assessed through the plots that I just showed of the many different vessels crossing the site. Also, we have to assess the likelihood of any vessel breaking down, because vessels don't just drop their anchors anywhere. If they need to drop an anchor and hold position under normal conditions, they'll go to a charted anchorage. So they'll only drop an anchor in an emergency if something's gone wrong. And also, we need to assess the water depth. Many vessels, vessels will have a limited cable length for their anchors, and so if the water depth is deep enough, the anchor simply won't touch the seafloor. Secondly, we need to assess the size of anchors. The bigger the vessel, the bigger the anchor. It's pretty much as simple as that. And thirdly, we need to assess the type and size of the anchor and the seabed material to understand how deep into the seabed different anchor sizes will penetrate. With all of that, we basically come up with a solution that we only need to bury the cable deep enough to avoid anchor strikes from the most frequent vessels that visit the site, and can accept the risk associated with low probability vessels, and so that limits the amount of cable burial that's required and keeps projects like offshore wind farms more economic, and ultimately keeps the price of electricity as low as possible. So following those short examples is just a final slide on what sort of people do this sort of work. Well, as per the themes of the previous slides, a range of marine geoscientists are required, from geotechnical engineers, so those are engineers who deal with soil conditions, geophysicists who employ the techniques shown in the previous two presentations, geomorphologists who detailed characterization of the seabed and basically read the seabed features to tell the story that it's to understand the story that it's telling. Mathematicians and risk analysts for advanced numerical assessment, and geologists to understand the depositional history and what's created the sediment that we see in the marine environment. So a whole range of people coming from a whole diverse range of backgrounds to get to do work in the marine geoscience environment. And that's my final slide. I'll hand back to Iris. Thank you.
That's brilliant, David. Thank you very much. So the final talk of today is from Natasha Barlow. She has got A-levels in geography, biology, chemistry, and art. She did her undergraduate in Durham in geography, and she also did her PhD at Durham as well. At the moment, she is working as an associate professor at the University of Leeds, working in environmental change. Before Leeds, she was at Durham, where she did research on sea level change, using the past to understand the present. So, Natasha, when you're ready, please share your slides. I just wanted to remind everyone there's questions coming in on the Q&A, so please, if you do have a question, feel free to submit it. And for those of you who joined a bit later, you can also, and who are watching on YouTube, you can also send your questions on Twitter or Instagram or email. So Natasha, when you're ready, take it away.
Great, thanks very much, Iris. So yeah, I'm going to kind of try and wrap up a little bit of kind of some of the stuff we've been seeing so far, and in particular picking up on David's final points there about the skills needed for marine geoscience, particularly from people who work in geomorphology and geology, geography, such as myself. I'm a geographer who now works in the geology department. So it goes to show that you can take some skills and apply it into different areas. You don't need to think, I need to choose the right thing. You know, you could do physics and then move into this space, for example, as well. And show that submarine landscapes really are a foundation for the net zero future that we really need to hit. So the first thing to declare is I really love mud, and I guess that's really how I found myself in this position. So this is a whole series of photos from me. I think all of these are actually from Alaska, where I first started my career working onshore. And then since moving to the University of Leeds, I found myself more and more working offshore, and I guess as a result can now call myself a marine geoscientist. So Katrine touched on this in her talk, that in the past we've had periods where ice sheets were really much larger than they were today, with ice covering places like the northern parts of the UK and also Scandinavia and North America. And this has happened over the course of the last 2 million years and caused quite a complicated sedimentary history on many of our continental shelves, of which many of us now study using the techniques that Michael outlined at the beginning. And just to reacquaint yourself, that's the ice sheet covering much of the UK. So at the University of Leeds, we were just south of the ice sheet margin. We found ourselves in a nice little enclave of ice-free land. But just to the north of where I live here, I'm right on the margin of that former ice sheet. So what does that mean for our submerged landscapes? Well, Katrine already showed you that we have records of ice sheets advancing and retreating through the offshore environment. So I'm not going to talk about that anymore, but I'm going to talk about those landscapes that then result when that ice retreats. So in particular, we see in the North Sea region, these large, flat terrestrial landscapes that were formed of peatlands and in which the rivers would have flowed across this landscape. So we didn't just go from ice to the North Sea, we went from ice to land, first of all. And the extent of that land can be shown in this map here by the browny colours, covering particularly the southern and the eastern parts of the North Sea and much of the UK continental shelf. And this land formed much of the environment in which early humans lived and formed a bridge between Europe and the UK. And we know this through archaeological remains that have been found quite extensively through the southern part of the North Sea, through dredging, through fishing, through archaeological surveys, but also in particular people picking up some of these pieces as they just walk along the beach. So once we're all allowed out and for me, I haven't been to the beach for 6 months, you keep your eyes open because you never know what you might find washed up. But then, of course, those big ice sheets that were fluctuating over North America and Scandinavia and parts of Northern Europe have, of course, melted. And Katrine talked about this. Of course, when we melt ice sheets, sea level, of course, rises. And in the consequence of the last ice sheet melting, that meant that those freshwater fluvial landscapes became flooded by the sea and eventually became coastal. And therefore, those communities that lived within the North Sea region eventually were flooded, and obviously that landscape wasn't available for occupation anymore. And of course, now the North Sea looks much like it does today. And you can see some of those kind of topographic highs within this imagery, particularly in the southern part of the North Sea and in the central part of an area called Dogger Bank, where we see these upland kind of features where the last of those human artifacts have been found. Now, of course, much of the North Sea is being exploited for energy, in particular for us to develop green energy resources. And, you know, David talked about some of the challenges there in terms of the hazards of employing some of these things. The thing that we're particularly interested in is that landscape that has changed through time, being glacial through to fluvial and freshwater, and then becoming coastal and marine, has left a really complicated sedimentary history. So history of all the different types of muds and clays and sands and peats that were deposited as those different environments went through the whole series of glacial interglacial cycles that we've experienced. This map here shows some of the locations where wind farm developments are either planned or currently ongoing. And I'm particularly going to focus on that Dogger Bank location, that topographic high within the central part of the North Sea, and just give you one example of the sorts of things that we found in some of the research we've done there. So this is Dogger Bank here. This is a couple of the wind farm areas that are currently either being developed or being developed. And by using those survey methods that Michael outlined, we're able to image that subsurface. And I think if you kind of get your eye in here quite quickly, you'll start recognizing in the graphics at the bottom, in the sort of purpley colors, features that look like if you draw a cross section of a river, right? With things like braided bar features and foul legs on one side versus the other, the sort of thing that you would have seen maybe if you've done GCSE geography or doing geography at any part of the stage where you might have drawn these features. And if we take lots and lots and lots of these images, exactly as Michael outlined, we can actually build up a picture in 3 dimensions of these cross sections. And we get these really cool images of basically these rivers that once flowed under this landscape that's now submerged by the North Sea. And this is an example here of one of the rivers that we found in this area. And we can do this for various parts of the North Sea. In particular, this is an example from Dogger Bank, and we can look at all the different layers. I focused on the river layers, but we can look at all the layers, the glacial layers, the freshwater layers, and the coastal layers, and we can build up a picture of how that landscape has formed and evolved over time in response to climate changes. So in response to the ice sheets forming over those landscapes, leaving very complicated, compacted sediments, and then as they retreated, leaving possibly lakes and leaving lake sediments, and then over time the rivers, which I've shown you, and then eventually being flooded by the modern sea as the large ice sheets finally melted. Why does this matter? Well, we need to put these wind turbines somewhere, and most of the wind turbines we have, particularly in UK waters, and quite a lot of the wind turbines that are currently being installed around the world, require their foundations to be buried within that mud and sediment. And in the UK government target is to power every home with offshore wind energy by 2030. And this was set out by Boris Johnson late last year as one of the sort of main ways we can try and get out of the economic crisis that COVID has left the country in. Importantly, though, it's not just a case of putting these wind turbines in, but we also need to replace old turbines. Some of our turbines in the ocean have now been there for 20 years, and they're actually getting ready to a point to be replaced. And the same will happen for anything we start to install now. In 20 or 30 years' time, they'll need replacing. So it's not just that we need this information over the next 10 years to reach this goal, but that technology will need to keep being replaced and updated. And often those turbines are getting bigger and bigger and bigger. So the complications that David outlined are getting more and more complicated. This is an example of one of those monopiles that are currently drilled into that sediment. It's huge. I think this is a great image. It gives you a really good idea. When you see those wind turbines out in the North Sea, you think, oh, that's kind of big. But when you see this guy standing there next to you, like, this thing is massive, okay? And therefore, if we drill this down into all of that sediment, we really, really need to understand it in detail. Not just for the cable laying, but to also know that our monopile and the base of our turbine is really secure, so that it doesn't happen that things like it falls over during a storm, as happened in that oil rig. And also that it's sustainable, so those things can be there for 20 years and work well without regular need for maintenance. And maintenance is one of the biggest costs currently to the cost of electricity that David showed in the beginning of his talk. So this is an example here, just a schematic of the depth of one of those monopiles going in about 40 meters below the seabed in Dogger Bank, going right down into those glacial sediments to the top, and then also into the shallow marine sands above. And every single turbine location in the North Sea is different, because that history of the ice advance and retreat and the rivers that came and went and the sea that overtopped all of that has left a really, really variable signature. And that means we need to understand those features in every single individual location. That allows us to then use all of that geophysical data that Michael outlined at the beginning, so that we can do some cool understanding of the Earth history that Katrina and I are particularly interested in, but that we can produce geological models and develop geotechnical models to allow this infrastructure to be put in safely and allow us to try and meet these net zero futures. So just to summarize, really, I think it's important to say that the future of net zero is in the hands of marine geosciences. Thanks.
Fantastic. Thank you very, very much, Natasha. So we have got loads of questions coming in on the Q&A right now. So I guess we'll just start with the most popular one, actually, from Millie, who is asking, are there any universities and university courses you recommend if someone is interested in marine science or marine biology? And I think that also allows me to add a little bit of information that I kind of forgot to mention in my introduction, which is that there are actually a lot of different pathways to becoming a marine geoscientist. You can see from our panelists, most of them have done earth sciences or geography, geology. But there is actually, and as David's slide showed really nicely, there are actually loads of different people working in marine geoscience. There is physicists, engineers, chemists, so lots of different options and different pathways into it. But if you are specifically interested in marine biology, for example, there are also university courses in marine biology directly. I don't know if any of the panelists want to add anything to that, specific tips?
So marine biology and marine science, you can find lists online for all of these, but particular strong universities for that are places like St Andrews, Newcastle, and Southampton. They are particularly strong in those areas. They kind of more focus on the biological processes than maybe some of the stuff that we've touched on today in regards to geosciences and the backgrounds that we have all had.
I would add to that don't just be interested in a technique as such, but also in an environment. So think of the environment you want to reconstruct, because as you will study, say, marine biology, as you know, in Bangor University, for instance, you will have a little bit of chemistry. You'll also have a little bit of earth sciences, because you cannot understand a marine environment without actually having a good understanding of all the processes that will affect that marine biological life. And so, yeah, think of that environment and think how you might want to better understand. And I think go from there and let that decide, you know, where and what you study.
Thank you very much. I think the next question is a really good one as well. Oh, it's swapped around on the Q&A. So, but I think I'll go with Emily's question and then we'll answer Fleur's question. So, what is a typical day at work for you? So maybe if each of the panelists could quickly comment on that. So maybe starting with David.
So it's a balance between technical work, so doing analysis like I showed, and fielding proposals, so requests for prices and descriptions of method statements, essentially, of how we'll do new work, which we hopefully win. So yeah, I guess ultimately we have a business to run, and so we have to get the work in for a fair price, and sort of say what we're going to do.
Brilliant. How about you, Michael? What do you do every day?
I'm going to answer this question before COVID, because obviously all of our lives have changed quite a lot, and now I spend my entire time talking to other people on on Teams and Zoom. But certainly before COVID, I spent a lot of my time traveling around the world, talking to different stakeholders, different clients about their requirements for offshore survey requests. I spent a lot of my time coming up with innovative technical solutions to try and, as David said, help run a business and help provide a commercial service to people. But I also spend a lot of my time strategizing, looking at different market trends, looking at different areas of the world where our services might be required, looking at different industries, be it offshore renewables, oil and gas, environmental, whatever it might be, and trying to work out where best to apply our technology for the greatest gain.
Brilliant. Katrine, what do you do every day?
Well, every day is very different, and I think that's what we heard already so far, and I think that really makes the job interesting. So even in academia, every day will be different. Sometimes you'll have to do a bit of marking, lots of feedback to students' work, but other days, you focus on a grant proposal or you study something. Today I had a meeting on how we will organize our ship time in June. Yes, and then you do video interviews. You prepare for a conference, somewhere. Again, pre-COVID, we would also be traveling to meet and greet and present our research. So it's teaching, it's research, it's some administration, a lot of student support. And yeah, I think really versatile. That's what makes it interesting.
Brilliant, thank you very much. Natasha?
Oh, well, as an academic, my life looks quite similar to Katrine's, because that's kind of what we do. But I guess if I was to focus on the research side, it might be that I spent the day in the laboratory preparing some samples or looking at some cores. I spend quite a lot of time looking down a microscope normally. That's not very COVID friendly because we're very close to the same piece of kit, but normally I would do that. So I particularly look at little algae that live in the sediments, or picking samples to be sent off to other labs, and also collaborating with lots of other researchers. I think the point that's being picked up here is we all have different skills and different interests, and therefore we can't target any of these problems on our own. And that's one of the real fun things about the job, is working with and meeting lots of cool and varied people and learning from them.
All right, thank you very much for that. So the next most popular question is from Fleur. She's asking, in terms of global location, where do you think is the most important place in the world to be working and studying as a marine scientist? So I don't know if, Katrine, do you have any idea about this?
I raised my eyebrows, I didn't. Well, I just wonder whether that is so crucial in the end. You can travel to where you need to be for your research, like we travel, for instance, to Antarctica. That doesn't mean you have to be there to study the entire time. I think you can get your knowledge from wherever you are. Even now with COVID, it seems that even from home, we can acquire quite a lot of knowledge and even nurture networks and yeah, collaborate together. So I don't think location is necessarily something that holds you back. That's nice and inclusive, but I think it also gives you an opportunity, because the marine world is everywhere. It does give you an opportunity to study this exciting topic wherever you want. So, it doesn't hold you back, but it does give you an opportunity to do something exciting.
Thank you very much. Do any of the other panelists have anything to add to that question?
I thoroughly agree.
Yeah, I think it's definitely, I agree as well. There's a lot of, opportunities to collaborate and do field work, get your data from all over the world, really. So thank you very much. The next question is from an anonymous attendee in the Zoom meeting. They're asking, would you say that this area of marine geoscience, science, geography is competitive in terms of jobs? Is it difficult to get a stable career even if you have the qualifications? Michael, do you have anything to add?
Yeah, I would say that certainly all of my classmates at school and university all went on to get great jobs, either in academia or in the commercial sense. One thing that is important to note is that particularly in the commodities market, so oil, gas, offshore work, offshore mining, the industry is very cyclical. So, you know, as you know, when you hear it on the news, or you drive to the petrol station, or your parents drive to the petrol station, and you see the price of petrol go up and down, that's because the price of oil is going up and down. So naturally there is fluctuations in the busyness of our industries. However, what I would say is, with a good grounding in the basics of geoscience, that there are so many different possible career paths that you won't ever struggle to find gainful employment. You know, there are lots of different options. People are able to spread themselves to lots of different types of job, lots of different types of company, and lots of different places, as we just heard. So I would say that, yeah, geoscience, there's always going to be the need for geoscientists, and there's always going to be employment opportunities all over the world.
Thank you very much. Any of the other panelists want to add anything to that?
The thing to probably add is that geoscience is underpinned by STEM subjects, and we all have a STEM background. Yes, I did do art as well because I enjoy colouring in, but therefore you have transferable skills. So if you come and do geosciences at university or an associated course, you have skills in mathematics, or you have skills in spatial analysis, data analysis, presentations, etc. And therefore you can use those to move into all sorts of industries. So it might be a great thing that you'd be interested now, and obviously a lot of you might be making that decision at 17 or something. Come and do what you enjoy, and if you end up in 20 years' time doing something different, you've got a great skill base to build upon. Don't feel that you're wedded to it for the rest of your career.
I agree. We monitor the graduate outcomes, and in fact, on the geosciences side is one of the best of the whole university. There was never a struggle to get a job.
Thank you very much. So the next question coming up is related to that, I think. So it's another anonymous attendee who's asking, are there any projects you recommend to allow young people to learn more about marine biology in relation to climate and work with scientists? So perhaps, Katrine, do you want to add a bit more to that?
There are internships available. I know there's a Nuffield scheme, and I've actually had A-level students in the lab with me for many years. I think, yeah, now we've had to stop those, of course, but I did, Flume Lab experiments with A-level students, and they were there for 3, 4, 5 weeks with me. And there's other schemes. I've even had internships at that level from abroad. So yeah, have a look at these schemes. There are out there, and contact the people in the university and say, hey, do you need a hand? I'm very willing to help you out, because there's so much work, like Natasha says, you know, there's so much analysis to be done, so many observations to be made. You know, we love it when people come and give us a hand, and at the same time, you learn a lot as you do so.
Fantastic, thank you very much. So the next question is from Rory. It is, what role can marine geoscience play in understanding ocean salinity and its role as a sink for carbon and the impacts of climate change? So maybe Natasha, do you want to answer that question?
Yeah, that's a great question, actually, Rory. I thought that was really insightful. So Katrine mentioned this, that if you go and do geosciences at university, you will be trained in a whole range of different things. It'll depend on which university you go to, but one of the things in particular at Leeds we do is do a lot of stuff in geochemistry. And really it's our geochemists that understand if we put carbon into the atmosphere, into the oceans, what that might mean. And also if we release carbon from our oceans. And actually it's something that we're really targeting at the moment. Is I mentioned to you very briefly all the peatlands that would have formed once the ice sheets retreated. We're really interested to understand if we erode that peat out due to changes in storm events, for example, and some of the sediment mobility processes that David highlighted, we're going to move carbon that's currently stored in our seabed and dissolve it into our oceans, and potentially in time release it into the atmosphere. And whether it's in the oceans or whether it's in the atmosphere, it's got a lot of different variations. So we're doing that from my background in geography, with some of our geologists and sedimentologists, but also with our geochemists. And a geoscience degree will give you the breadth of that experience that will help you, go on and see whether that's particularly something you're interested in targeting, whether that be in a laboratory measuring seawater samples, or as some of my colleagues do, with being through computer modeling. And they do coding and programming, and they try and understand changes in the carbon cycle and the relationship with the oceans and what that might mean for future climate.
Fantastic. Thanks very much, Natasha. So the next question is from Charlotte, and she is asking, are you ever are you worried that dredging and sending sound systems down into the ocean will disturb the natural environment and the animals in the sea? So maybe David, that's a question you can answer.
Yeah, sure. Yes, and as an industry, we're certainly worried about that, and there's a lot done about it. We haven't mentioned it at all in what we've spoken about today, but any of these offshore developments undergo really rigorous consenting applications, which involve a huge amount of environmental impact assessment. That's sort of the first stage of a development. There are things such as marine mammal observers on board vessels when undertaking surveys to make sure that, yeah, for exactly that reason, that we're not upsetting the sort of wildlife that's existing in the area. And some of the sort of remaining problems, one of the big things that Natasha showed was the large monopiles that are used to support these offshore wind farms. The best way of getting those into the seafloor at the minute is to hammer them in. That makes a lot of noise, and so there's a lot of research in how we can improve that process. So yes, as an industry, there's a lot of concern. There's a lot of good stuff going on at the minute already, and looking into ways we can improve further.
Fantastic.
It's also worth pointing out that because we use sound at so many different frequencies, everything affects things slightly differently. So there are some damaging sound waves for certain marine mammals, and as David said, we work very hard to limit those and to reduce the impact on the environment. But there are also some sound waves that animals actively enjoy. I've been working on boats off the coast of Scotland where we've had pods of dolphins follow us around all day with our equipment going because they genuinely enjoy it. So yeah, we work very hard to limit our impact, but some of the things we do are actually quite good fun for dolphins and whales.
That's a great fact, Michael. I didn't know that was happening.
It's really irritating because you pick them up on the data and they obscure interesting things that you're meant to be looking at.
Oh dear. So it's kind of a follow-up question, I think, from that. So Gracie asking in the chat as well, if you ever consult with specialists as well on marine wildlife. So I think that's kind of covered in that. And I guess, David, that's what you were saying when you're doing more research and into the effects, then specialists are involved in that, I would imagine.
Yeah, absolutely. One of the parts of my work is to manage sort of spatial database systems of all of the research that's been involved to date on a development, and probably the largest sort of section in that is on the wildlife that may be affected, and so all sorts of environmental specialists would be feeding in information about birds, fish, habitats of all sorts. So yeah, getting the right specialists to advise as best as possible.
And also, very interestingly, you need archaeologists, right? Because David will know that all of these developments require archaeologists because of all of the human occupation and stuff that I pointed out. So it goes to show that linking up with all these other specialists is really important. I don't think many people realise that to build a wind farm in the North Sea, you need an archaeology assessment.
That's very, very interesting. So moving back slightly to degree programs and what you need to become a marine geoscientist. So Maddie is asking in the chat, what are the benefits from studying marine biology with oceanography compared to just marine biology as an undergraduate? Katrine?
Sorry, unmute myself. Yes, I think if you want to understand the marine life, I do think it makes sense that you understand the environment that they live in and that they depend on. And then the oceanographic part really does come in. You know, we offer both, and I'm sure other universities do as well. But I see that the career paths are a little bit more open. I think with marine biology and oceanography, we have people who end up working for the Met Office because they really like the oceanographic part of it, and they still use it to project what might happen to marine life, but by actually focusing on how ocean processes will change. Coming back to the climate crisis, that will impact those ocean processes, and that will then therefore impact the marine life. So I think there's a piece of the puzzle there that you can't ignore. So yeah, that's just my 2 pennies.
Fantastic. Thank you very much for that, Katrine. So we'll move on to the next question from Holly. She's asking, how long on average each year do you spend abroad or conducting field research? So maybe Natasha wants to say something about that.
Sure. So as an undergraduate, it will vary based on your degree that you decide to do. So some of us teach on programs, well, I do teach on a program that's supported by the GeoSoc, so that is the Geological Society of London that we've been talking about, and they require you to do, at the moment, about 40 days of fieldwork, non-COVID, right, across the course of your degree. That varies. So I did geography, that's not the same requirement. I probably did, I don't know, 6 weeks or something in total, I would think. But then as a PhD student, I went to Alaska for at least 5 weeks every year for about 3 years. And then when I moved on to becoming a postdoc, I traveled for nearly 6 months of each year in different periods because it depended on where my fieldwork was. Whereas in the last 2 or 3 years, because of working offshore, I haven't traveled anywhere near as much. So it really depends on where your questions are and what specifically you're needing to do. And I think the thing to bear in mind is you don't have to do that. So for some people, some of our graduates go off and live in a tent for 3 years in the middle of nowhere, doing exploration geology, for example. And that's what they love to do. But it's not, you don't have to at the same time. So if you're not somebody who enjoys doing that, you still can get into this field. And a lot of the remote imaging that, you know, Michael introduced is allowing us to do a lot of these things from home. So it's very much up to you and the pathway you're interested in, the questions you're interested in. Don't feel you have to spend months abroad or that you have to spend all your time at home. There are routes for everybody.
Fantastic. Does Michael or David maybe want to add something to that?
Yeah, I completely agree. I mean, I've worked offshore in my career where I've spent, you know, a month or two away from home at once. You know, but that's entirely my choice. I also have colleagues who, you know, never go away, you know, spend every single night in their own beds. So as Natasha was saying, with the increase in remote technologies, with the increase in, you know, video conferencing and the ability to conduct your work and your research or your job from pretty much anywhere with an internet connection, the chances are you can almost design your own ticket. Having said that, if you do want opportunities for travel, there are a huge number in geoscience, you know, a massive opportunity for travel in geoscience. Because as we've already touched on in an earlier answer, you know, there is the need for geoscience everywhere. So there's always going to be places you can go, people you can visit, institutions you can collaborate with. So yeah, the answer to that question is exactly as much travel as you want, from 0 up to 100%.
Fantastic. Thank you very much. I think perhaps one more question before we wrap up, because it is almost time, at least on my watch here. So one more question, and perhaps quite an interesting one, is what kind of money do you earn in this industry? David?
David.
It ranges hugely, but it can be, you know, 6 figures if you really want it to be, and if you're very money driven. As a graduate starting out, you could expect, I don't know, somewhere 20 to 30,000 if you're willing to go and work offshore on a monthly basis, as lots of survey contractors require, you know, so to spend time away. You'll often have a sort of bonus associated with days offshore, so that can be quite nice when starting out. It was certainly a positive for me, and a big incentive to go and sit on the boat for 6 weeks just to try and bring a bit more money in. But you know, if money is the absolute goal, then you can certainly seek out a nice large salary.
That's exactly what I was going to say. You know, my boss is a millionaire, and you should see the car he drives. I'm definitely not a millionaire, but the point is, as David says, you know, as with the amount of travel, you can chase exactly what you want. You know, you can chase a different lifestyle, you can chase a different career path, and ultimately everything comes down to what you make it. There are opportunities abound.
Brilliant. Thank you very much to all the panelists for answering the questions. Unfortunately, our time is up. So thank you very much to everyone who presented today. Thank you very much for everyone who joined in. I hope you enjoyed it, and we'll hope to see you for the second webinar very soon.
Thanks, everyone. Thanks for your questions.
Bye-bye.